Instrument transformers supply protective relays with current and voltage for measurement. This high current and voltage is first converted by the transformers to much lower quantities that can safely be injected into the relay for measurement. It is important to note that the proper selection of current and voltage transformers for protective relaying applications is the responsibility of the system engineer. CT's introduction. The function of a current transformer, or CT, is to take a current flowing through a wire or cable and step it down to a magnitude that a protective relay can measure. A primary characteristic of CTs is their conversion ratio. In this example, our conversion ratio is 100 to 5, meaning that if 100 amps are passed through the primary phase wire, the CT will scale this down to 5 amps and direct it to the relay via the secondary windings. The 5 amp measure is known as the secondary nominal current. If a fault were to occur on this phase that increases the primary current to 200 amps, then 10 amps would be passed to the relay through the secondary windings consistent with the ratio. CTs have two types of secondary ratings, 5 amps and 1 amp respectively. 5 amps is typically the North American standard, while 1 amp is used in Europe and Asia. Primary ratings are available in various different levels, for example 100, 150, 200, etc. Types of CTs. A common current transformer construction is one in which the power system phase wire is passed through the hole in the center of an annular core or ring, which is called a window. This forms the primary winding. A second insulated wire is then wound around the core and then brought to the relay for measurement. This is known as the secondary winding. A CT with this type of construction is typically referred to as a toroidal or donut style of CT. A bushing type CT refers to a CT that is built into another power system device such as a breaker. Terminals are provided on these devices to permit connecting the CT to a relay. A bar type CT has a solid bar that passes through the annular core to form the primary winding of the CT. The primary phase wires of the power system are then connected directly to these bars to complete the connections. CT selection. Proper protection starts with the selection of current transformers. The following is a simple procedure that can be used to check whether or not there is the possibility of CT saturation. This procedure is as follows. The first step is to ensure that the primary rating of the current transformers is equal to or greater than the expected full load current. We can determine the primary rating of a CT by looking at its ratio. For a ratio of 100 to 5, a CT has a primary rating of 100, meaning that no more than 100 amps should be passed through the CT under normal operating conditions. The second step is to ensure that the CT can drive what is called the attached burden at the worst-case fault current levels without saturating. The burden refers to the total load resistance of the secondary circuit. The calculation for the burden is CT secondary resistance, which is the amount of resistance on the secondary windings on the CT, added to the connection wire resistance, which is supplied by the manufacturer, added to the relay's burden resistance, which is the resistance within the protection relay. As explained in the previous section, a CT becomes saturated when the voltage secondaries reach the knee point of the excitation curve. To determine whether the CT can drive the attached burden under worst-case fault conditions without saturating, we must determine what the CT's secondary voltage will be at the time of this fault. The CT secondary voltage at the time of fault is equal to the burden resistance times the maximum fault current divided by the CT conversion ratio. The resulting value is then plotted onto the CT excitation curve. If the value plotted on the curve is below the knee point, then the CT will not saturate under these worst-case fault conditions. If the value is equal to or greater than the knee point, then the CT will saturate. Now we will look at a practical example to help us further explain this calculation. Let's assume that we have a motor that draws a maximum full load current of 285 amps. The first step is to choose the appropriate CT. It is customary to select a CT that has a primary rating falling between 50 to 100% of our maximum full load current, in this case 285 amps. Possible CTs for this use would be 300 to 5, 400 to 5, and 500 to 5 CTs, because the primary rating falls between 50 to 100%. In this case, we would select the CT that would fall the closest to 100%. The reason for this is the higher the CT ratio is over the full load current, the less sensitive that CT will be. Since accuracy is always imperative, we will select a CT with a 300 to 5 amp conversion, where the primary rating is 300 and closest to the 100% primary rating. The next step is to ensure this CT doesn't saturate under worst-case fault conditions. If it does, a higher ratio CT, such as the 400 to 5 CT, may need to be chosen. The first step in determining whether a CT will saturate is calculating the maximum current that will appear on the primary of the CT under a worst-case fault condition. The maximum fault current at the load is determined by a fault study, and in this case was determined to be 6,000 amps. Next, we will calculate the secondary resistance, or burden, using the stats provided. The phase CT's secondary resistance, that is the resistance of the windings on the CT, is equal to 0.088 ohms. The length of each wire from the CT to the relay is 50 meters and has a rated resistance of 2.5 ohms per kilometer. The total burden is equal to the CT secondary resistance, which is 0.088, plus 2 times the lead length of 50 meters multiplied by the lead resistance of 2.5 ohms per kilometer, and then divided by 1,000 meters. This is then added to the relay burden of 0.008 ohms, resulting in a total burden of 0.346 ohms. Now the secondary voltage at the time of a worst-case fault can be calculated. First, the total burden resistance, 0.346 ohms, is multiplied by the maximum fault current, 6,000 amps. The result is then divided by the CT ratio, 300 to 5, concluding that the secondary voltage at the time of a worst-case fault is 34.6 volts. With the maximum secondary CT fault voltage calculated, the final step is to refer to the CT excitation curve. By plotting the 34.6 volts value on the excitation curve, we notice that it falls well below the knee point, indicating that it will not saturate under a worst-case fault condition. If the factors affecting the burden were ever to change, or a higher fault current is measured, these calculations must be repeated to ensure the CT does not saturate. Potential transformers. The next type of transformer we will cover is the potential transformer symbolized as PT, or sometimes known as voltage transformers symbolized as VT. Similar to current transformers, potential transformers scale down the voltage passed through them, as opposed to the previously mentioned current. The scaled-down voltage is then routed to a protective relay for measurement. Also as in current, a PT is classified with a conversion ratio indicating the amount the primary voltage is scaled down. For example, 60 to 1 scales the primary voltage down to 120 volts. There are 2 different types of potential transformers used today: the electromagnetic voltage transformer and the capacitive voltage transformer. Electromagnetic voltage transformers are usually used when accurate metering needs to be performed for lower voltage applications. Capacitive voltage transformers are commonly used in high voltage transmission line applications where the voltage is higher than 66 kilovolts. Electromagnetic voltage transformers have dense winding drops designed to accurately scale down the voltage and make sure the ratio is consistent for all variations in the input voltage. Due to the small amount of voltage drops per winding, the electromagnetic voltage transformers will increase in size as the rated primary voltage also increases. Likewise, the cost of electromagnetic voltage transformers tends to increase at a disproportionate rate to the primary voltage rating. Capacitive voltage transformers, or CVTs, are normally used on higher voltage applications. The CVT is basically a capacitance potential divider and consists of the following components: coupling capacitors, typically 10, compensating reactor, step-down transformer, and a ferro-resonance suppression circuit that is found just before the output terminals for connecting to a relay. The accuracy of a PT's operation is specified in the displayed label format. The first item in the label indicates the accuracy class of the PT. The 3 common accuracy classes are 1.2, indicating PT accuracy between 98.8 and 101.2%, 0.6, indicating PT accuracy between 99.4 and 100.6%, and 0.3, indicating PT accuracy between 99.7 and 100.3%. The next character in the label is a letter designating the burden rating. The typical burden designations and their corresponding ratings are as follows. The W rating indicates the PT will operate accurately as long as the burden doesn't exceed 12.5 volt-amperes. The X rating indicates the PT will operate accurately as long as the burden doesn't exceed 25 volt-amperes. The Y rating indicates the PT will operate accurately as long as the burden doesn't exceed 75 volt-amperes. The Z rating indicates the PT will operate accurately as long as the burden doesn't exceed 200 volt-amperes. And the double Z rating indicates the PT will operate accurately as long as the burden doesn't exceed 400 volt-amperes. If at any time the burden exceeds the PT's rating, the accuracy classification will be compromised. In this example, the PT rated 0.6 double Z would have an accuracy between 99.4 and 100.6% as long as the burden of the PT remains under 400 volt-amperes.